go on to the column experiments now. So this is what the column experiment apparatus looks like. It's basically the same thing that I showed you before for the proof of concept experiment, except at a larger scale. Here we use a larger diameter column and something that's about 15 centimeters tall. You can see we've fully outfitted it with thermocouples again. Everything else is pretty much the same. We have a bit more sophisticated gas analyzing system, so we can track carbon dioxide and carbon monoxide in real time, things like that. Now what I want to show you here, oh, this worked before I turned on WebEx, but now it's not working, of course. That's too bad. Let me go back and see if I can try. Ah, there we go. Okay, so on the left here is a webcam of the smoldering reaction. I'm going to pause this for a sec. Perfect. All right, so we see the front. Here's the unburnt fuel. Here is the burning front moving up. It's moving up fairly, you can see it's kind of a heterogeneous progress because this material, of course, is somewhat heterogeneous. We have airflow going up from the bottom, and here you can see the front. The nice thing is that even when you have a kind of heterogeneous front, what we found is that it doesn't really matter. The reaction will get to the top in the end, and it'll all be gone. Basically in the end. So even if it moves up faster in some places than in others, like it could be moving faster over here than over here, it all seems to get there in the end. On this side, though, it doesn't look nearly so heterogeneous. This is a thermal infrared video of the front. And so what we see is ambient conditions up here. Here is the heating front that I mentioned, the heating and drying front. Here is the oxidation front happening here, and here is the cooling that's occurring behind the reaction. So you can see that the front is not a very thin band. It's a bit thicker band than that. But you can see the band travel up through the porous medium at the same time as we visually observe the front. So I'll just get these two going again, and hopefully you'll see how these things move up through the reaction, through the porous medium, leaving the clean soil behind. Again, that's been speeded up about 50 times. For it to travel up through this 15 centimeter column probably takes on the order of about 20 minutes or so. So it's probably moving on the order of half a centimeter per minute, something like that. Maybe 30 minutes. Depends how, I'll show you what factors affect how long it takes. We can control that, in fact. So here is what we get from the thermocouples. Thermocouples are really a very critical instrument for measuring any kind of combustion process. It is your number one tool. And so we get very used to looking at these temperature. Here's temperature on the vertical axis versus, in this case, time. We could also measure as a function of distance, but here's a function of time on the horizontal axis. So you can see we had a period here of preheating where we had the heater turned on, but no airflow. And you can see we waited until the napple reached, these different lines are the thermocouples, where this one here is the one closest to the heater, and this one here is the one furthest away from the heater at the top of the column. So we're going from here, from up this line to this line, we're going up the column. Now, so what we see is that right next to the heater, we have 400 degrees Celsius, and that's when we decide to turn the air on. But as you go up the column, near the top of the column, we have essentially ambient conditions, and we have a temperature gradient up the column. And about half of the column is at less than 100 degrees when we turn the air on. And you can see that the first thing that happens is immediately we get this sharp spike in temperature, where it jumps from 400 degrees to almost 1200 degrees in just a few minutes. That slope here, this ramp, is classic for the onset of an exothermic combustion reaction, in this case a smoldering reaction. So you start the airflow and smoldering immediately occurs, and then very soon after it peaks, we shut down the heating element. So after that, we're only blowing air. And what we see is that the next location then peaks and starts to cool down. Then the next location peaks and starts to cool down, and the following location peaks and starts to cool down. And the fact that these temperature profiles are crossing each other, and that we have a peak followed by a peak followed by a peak, the sustaining of a high temperature peak and the crossing over of thermocouple profiles, those are extremely characteristic of a self-sustaining, propagating reaction. So we know that there's a self-sustaining reaction traveling up this column. Now here we see all the thermocouples going into cooling mode, and that's where the reaction has shut itself down. All the napple we know is gone, all the coal tar is gone, and so the reaction is cooling itself down because there's no fuel left. So it has this feature of being not only self-sustaining, but self-terminating. It shuts itself down, which is a very handy feature. Now, if we overlay on top of this the carbon dioxide that we've been measuring, here we see the ambient carbon dioxide, the background carbon dioxide, and then as soon as the reaction starts, we see this peak, this spike in carbon dioxide concentration being emitted from the column, and that's obviously the only thing that can produce that is an exothermic combustion reaction. So we're not volatilizing the material, we're actually combusting the material. And then after the napple disappears, you can see it slowly go back to ambient carbon dioxide. So that's the kind of data we get from all of our column experiments. And when we excavate the column, you can see that we can excavate this in little increments so that we get depth discrete samples all the way from the bottom up to the top. And here we see that the initial total petroleum hydrocarbon concentration for this coal tar contaminated soil, for this example, was 38,000 milligrams per kilogram. And the initial PAHs, the polycyclic aromatic hydrocarbons, was 9,500 milligrams per kilogram initially. And then you can see in our samples there's basically nothing there. It's virtually empty. In this case, we had a beige sand that turned red, and the red is the evidence of some iron oxidation that occurred as part of the reaction. So this soil gets a bit reddish. And that's been observed very common, for example, in forest fires. The soil in the forest fire can turn red. Okay, so that's a very typical type of result. But what I want to summarize for you now is over 150 laboratory experiments that we've been doing. We've been looking at a range of types of soils, a range of types of napples. We've been looking at the effect of airflow rate, the effect of soil concentration, contaminant concentration, and the range of water contents as well. So, for example, on the left here, I'm showing you the velocity of the smoldering front, so how fast it's propagating up the column, as a function of air flux. And on the left, we're showing you coal tar in two sands, a coarse sand and a medium sand. And on the right, we're showing crude oil, so a different material. And what you see in both cases, a very strong dependence on the injected flow rate of air. The higher the flow rate of air, this is basically, air flux is flow rate divided, so volumetric flow rate divided by the cross-sectional area of the column. So you can see that as we increase that, we basically get a linear increase in the velocity of the smoldering front. For both these cases, a linear increase. And remember, velocity is proportional to the rate of mass destruction. So if you want to clean your site faster, you blow the air harder. That's basically what we're showing here. And you can see the velocities range between about 0.2 centimeters per minute and up to 1.2 centimeters per minute. So that's quite a range of velocities, given that our column is about 15 centimeters high. You can really dictate how long it takes to treat that column by controlling the airflow rate. And unfortunately, it's not shown here, but I'll just mention it briefly. Some experiments we did where we started the reaction going halfway up the column, we then shut down the air to see what would happen, because there's a lot of concern by some people that there might be a reaction that can't be stopped, a sort of a runaway reaction that goes on for years and years and we have no control of it. But that does not happen with STAR. It's basically the heat capacity of the napple in the soil is such that if you stop delivering the air, the reaction immediately shuts down. And it basically extinguishes itself right where you've turned it off, right where you've turned off the air. Now, while I mentioned that, I will say that if you don't wait too long and turn the air back on, as long as the material doesn't cool too much, if it stays above the ignition temperature, so say it cools from 800 degrees down to 400 degrees, you turn the air back on, it will start up again. So, for example, in one of our ex-situ tests, one of our pilot tests, we had a blower failure, and the blower went down, and we had to do some rewiring and get it back up again, and we managed to restart the reaction without adding any more energy. So that's pretty cool. Let's see. Here what we're showing you is the peak temperature, so the peaks of those thermocouple profiles I've shown you. What the average peak temperature is a function of airflow rate. And you can see there is a small dependence on airflow rate. The blue dots here are coal tar. The red dots are crude oil. So we see a small dependence on airflow. You increase the airflow, you get slightly higher peak temperatures. For coal tar, you can see the peak temperatures range between about 800 to about 1100 degrees Celsius. So it's very hot, very exothermic reaction. And that's because coal tar is a very complex long-chain hydrocarbon. There's a lot of heavy molecules in it. Crude oil, you can see, has a characteristic lower burning temperature between 600 and 700 degrees Celsius. And so it's also a heavy hydrocarbon, but not quite as complex. It has a wider range of hydrocarbons and maybe not as many hydrocarbons that are greater than perhaps C35 than as much as coal tar does. So what we see of STAR is that each fuel has its own characteristic combustion temperature. And of course, the lower combustion temperature means less energy released, but also it requires less energy to combust. So, so the energy produced matches the energy it needs, of course. Here's another interesting result. This is the velocity of the smoldering front again in centimeters per minute as a function of the concentration of the napple. So here we're looking at very low, 25,000 milligrams per kilogram is still pretty highly contaminated material. You have to keep in mind that, for example, if you want to clean up your site for no further action required, you're going to have to get it down below 5,000 milligrams per kilogram. So 25,000 is still pretty contaminated, but here we're looking up to as much as 150,000 milligrams per kilogram, so that's almost saturated soil. Almost no air porosity, almost all of it occupied by napple. And you can see there's actually very little dependence on, the front does not move faster or slower if you change the concentration. Basically, as you increase the concentration of napple, you are generating more energy. There's more fuel there, but there's also a higher heat capacity. There's more energy that's needed to get that material up to ignition temperature. So basically, there's a balance there between the energy produced and the energy absorbed. And remember the equation I showed you for the smoldering velocity? Well, basically, there's a balance there in that reaction, and we're not getting any faster velocity or any slower. Now, the other thing that's interesting to see here is that we have these open circles, and those are basic experiments that were not self-sustaining. So basically, we're seeing that down around the 10 to 15,000 milligram per kilogram range at the scale of a small column, the reaction, we can start it, but it does not become self-sustaining and the reaction dies. So one thing that's interesting for STAR, which is not true for most other technologies, is that there is a minimum concentration that you're going to need to have a self-sustaining reaction. Now, so that means you can't have too little contamination. You need to have some kind of substantial contamination. Now, at the column scale, remember I said that's the hardest scale to ignite a reaction. So we're seeing maybe 10, 12,000, 15,000 milligrams per kilogram, even up to 20,000 here, where we couldn't get smoldering to be self-sustaining. But we expect it, for example, at the large scale, we expect that to be much lower. It could be on the order of 5,000 milligrams per kilogram. We don't really know. We haven't had a chance to test that yet at the large scale, but we suspect that it would be much lower because of this. There's much less heat loss to the outside world. Here's average peak temperature as a function of the initial water saturation. So now we're mixing coal tar with sand and also with water. So we've got zero water here. That's what we've seen before. And here's average peak temperature. So on the left, the red squares are for coal tar, and they're plotted on the left axis here as peak temperature. And you can see as we get more and more water, and here, in fact, at 75% water, we have 25% napple and 75% water and 0 air porosity. You can see that we still get self-sustaining combustion in every case. We get basically a little bit lower peak temperature because the water is the energy required to boil off the water ahead of the front is taking away some of the energy. So that reduces the peak temperature. The blue circles are plotted on the right-hand axis, and that's the smoldering velocity. And you can see that we are getting a decrease in the advancing velocity with increasing water saturation. So the front can't travel as quickly, but it's still propagating in a self-sustaining manner, and in every case, the soil is completely clean at the end. It just means that some of the energy, that means that there's excess energy in the fuel, and some of that excess energy is being used to boil off the water. So, what can we conclude from all of these experiments? We saw that at the column scale now, at the column scale, we've got, we did experiments, I didn't show you these, sorry, but we have silts, sands, a range of sands, and up to gravels, all that worked effectively. The problems are expected when we have clay, because clay is relatively impermeable to air, as you know from the in situ air sparging lectures. And so smoldering can happen in clay, but it happens extremely slowly, if it happens at all. You have to deliver at least a minimum amount of air to get smoldering going. It could be a very small amount. But the other issue with clay is that, of course, at certain temperatures, it will melt. So if you get it hot enough, you can get it to fuse. So clay is anticipated to be an issue. The other issue is cobbles. If you have two large particles in a scale of a column, then the cobbles they absorb too much energy from the front, and it can make the front extinguish. Now, these are things that we saw at the column scale. In fact, I can tell you now that we've done an experiment, an in situ pilot, that I'll talk about soon, where there was bricks. And the smoldering traveled through the bricks. It was napple penetrated through a bunch of bricks where a building had been knocked down. And it traveled through bricks no problem. So it's all a function of scale and heat loss. Okay, we've looked at a whole number of industrial liquids, coal tars, creosotes, petroleum hydrocarbons of different types. But what we anticipate is that very volatile compounds with low boiling points, such as diesel, gasoline, and chlorinated solvents, all could be very challenging because, of course, they volatilize so fast, they volatilize ahead of the front, just like the water does, and it's very hard to have a self-sustaining front. At the end of the lecture, however, I will show you that we have managed to smolder chlorinated solvents, and I'll show you how we've managed to do that. We've shown that airflow is a key controlling parameter, particularly affecting the rate of mass destruction, or the rate that the front travels through the porous medium. And we see that the reactions completely shut down when we terminate the airflow. The reaction also shuts down when all the napple is consumed. We've looked at, in these suite of experiments, we looked at between 15,000 and 145,000 milligrams per kilogram of TPH being destroyed. So we can handle very, very contaminated material. But we see a problem when we have less than 10% of the pore space occupied by the napple. So that can be a challenge. And when it comes to the water content, all the water contents we tried, at the column scale was no problem. It would always drive a boiling front ahead of the smoldering front. What we didn't know at this point was how would it work in the field when you actually have a groundwater table, and when you're below the water table and water is trying to flow towards your reaction at the same time the reaction is moving outwards.